Hello everyone, this is Athota Rathan Babu, working as an assistant professor in the Department of Aeronautical Engineering, and I am dealing with the course Computational Aerodynamics. And in today's topic, we will see what is the significance of partial differential equations. So, how partial differential equations play a major role in computational aerodynamics and computational fluid dynamics. So, why do we learn them actually? And one more thing, so how do we divide the flow characteristics based on the partial differential equations? So low speed flow, high speed flow, let's say subsonic flow, supersonic flow. So these things we will have to see based on the partial differential equations. So about that we will learn in detail. So first we will just see what is Mach number. We'll just recall. So why? Because in the partial differential equation we will use low speed flow, elliptical equations, parabolic equations, and hyperbolic equation. So as a prerequisite, like you should know what is basic Mach number actually. So we'll just recall and we'll see their categorization. So already we have seen Mach number is equal to V by A. So which is velocity of the object, or let's say velocity of the flow. So in that medium, so whether you take water, whether you take air, so the corresponding medium in which the body or the flow is traveling, so that velocity is this one. And A is nothing but speed of sound in that medium actually. So based on these things, so basically this is the velocity of the object and this is the speed of sound. So when the object is moving in air or water, so it emits sound waves. So that sound wave, so when it is traveling less than the speed of the body, then Mach number will be greater than 1. So if that sound wave travels faster than the speed of the body, then the Mach number is less than 1. So we are correlating or relating between the velocity of the object and the sound wave. So example, like you can observe daily life aircrafts or airplanes. So when a person standing on the ground, when aircraft makes noise on the sky, so he will think that it is on its overhead. So but it will be somewhere in front of him actually. Why? Because so the speed of the aircraft is more than the speed of sound. So that's why by the time the observer see the aircraft, it will not be on his overhead. So this is one of the realistic example. And similarly, we can take a realistic example of water. And when you throw a stone, what happens actually? The waves. So it will repel actually. So there also you have sound waves. And similarly, a person making a noise in an empty room, so the sound waves will travel. A bomb blast, the sound waves will travel. So basically, there are so many examples of sound waves traveling. So when we take that sound wave and when we take that object motion, so based on this relative velocity, so there is one more wave which is forming called shock wave. So when body velocity is greater than the speed of sound, there is a wave which is formed called shock wave. So that shock wave is formed because of collection of all weak sound waves. So this all weak sound waves. Why we call weak? Because the body velocity is more than the speed of sound. So therefore, what happens actually? All the waves will travel together, sound waves, and collect a near a region. So which will form a very thin layer. So which is called a shock wave. So this shock wave actually will try to reduce the velocity of the body. So it is like a marathon kind of thing. So where let's say V is nothing but velocity of the object. So A is nothing but the speed of sound. So when the velocity of the object is increasing and speed of sound is less than the velocity of the body, so ultimately the sound wave will try to reduce the velocity of the object by creating the shock wave. So when a shock wave is formed, so the corresponding drag is a resistive force which is offered by the fluid medium. So that drag is nothing but wave drag. So wave drag is created when the velocity of the object is greater than speed of sound. So what is the purpose of wave drag? So the wave drag will reduce the velocity of the object actually. Okay, so somehow the sound wave wants to reduce the velocity of the object. Why? Because it has the increased its speed actually. So that's why. So it's all coming because of the nature effects. Now we have seen the characterization of the Mach waves. We say that if Mach number is less than 0.3, the flow is incompressible. If Mach number is in between 0.3 and 0.8, so the flow is called subsonic. Subsonic. So this is incompressible, and we say it is low speed also. So we can also say it is a low speed flow. Okay. So basically in this zone, so if the flow has a Mach number less than 0.3, so the density variation, so basically density of that medium will not change with respect to space or time. Okay. So basically flow parameters: pressure, density, temperature, velocity. So these are the fundamental flow parameters, so which will depend on time, so x coordinate, y coordinate, and z coordinate. Okay. So when the flow is incompressible, so we say that the density parameter will not vary with respect to both time and space coordinates. Okay. Now when the flow crosses Mach number 0.3, so the compressibility effects will come into picture. So when the fluid get compressed, so the molecules, so basically you take a molecule of air, another molecule of air, so when they collide with each other, so when they get compressed, so what happens? So there is a temperature rise in that flow. So you take an empty room, so you say that some molecules are present, some air molecules. So what happens actually? So these will have random motion. So when they go with high velocity, what happens actually? They collide with each other and they vibrate. So when the flow speed crosses, let's say 110 meter per second, example, so they collide with each other, and there is a rise in temperature actually. So this rise in temperature will actually change the properties of the fluid flow actually. So if it is less than point mark 0.3, then it is negligible actually. So the average properties will not change. So when we say average, so all collection of the particles actually. Okay. So this is one thing. And when Mach number is in between 1.2 and 0.8, so we call this region as a transonic region, so which is upper subsonic and lower supersonic, so which is the transition between the subsonic and supersonic. So this is called transonic zone. Okay. So if Mach number is greater than 1.2 and less than 5, so we say this one as supersonic actually. So in this zone, so in the transonic zone and the supersonic zone, so the speed of the object or the speed of the flow has crossed the speed of the sound. So in the subsonic, you don't have any shock waves formed. Why? Because the speed of sound is greater than the speed of the flow or the object. So therefore in these zones, so you don't have any shock waves. So in these zones, transonic zone, supersonic zone, and here we have one more parameter which is called hypersonic, which is greater than 5. So we call it as hypersonic. Okay. So in the hypersonic zone, so we have the breakage of molecules. So basically the oxygen atoms, they will break and they will form an nascent oxygen. So this is what happens in the hypersonic flow. So we have incompressible low speed flow, we have subsonic flow, we have transonic flow, we have supersonic flow, and we have hypersonic flow. Now, so we need to identify so how the flow has going from, like, how the flow has passed from one region to other region using partial differential equations. So generally, we have a second order PDE equation. I'll just write down it. So we have a dou square x, sorry, so f by dou x square plus b dou square f by dou x dou y plus c dou square f by dou y square plus d dou f by dou x plus e dou f by dou y plus f, let's say plus constant, or you can take it as g and you can take it as h. So this is a general second order partial differential equation. So there is a difference between partial differential equation PDE and ordinary differential equation ODE. Okay, so this dou term is called partial differential equation. So when I say d, so let's say d square f by dx square. Okay, or this is called substantial derivative actually. So d square, this is called the ordinary differential equation, dou square f by dou x square. So can we see what is the difference between dou square f by dou x square and d square f by dx square? So what is dou and what is d actually? So when we use dou, so the major significance is, so the function f, in the f you can use any parameter. So the f can be any flow variable, which is you can take velocity, so you can take pressure, or you can take temperature, or you take density. So anything it can be actually. So let's say any flow variable you can take. So basically you take f is a function. Okay, so this f, if it is depending on more than one independent parameter, so basically we say that x, y, z and time, so basically they are called independent coordinates. So x will not depend on y, y will not depend on z, and this will not depend on time actually. So they are independent with each other. So when I say a function f is depending on x, y, z, comma t, so then we need to use partial differential equation actually. Okay, so in this case we need to employ this partial differential equation. Now when can we use the ordinary differential equation? So ODE. So when do we use? So if function f is only depending on only one independent parameter, so let's say 1D equation. Okay, so 1D study equation, so f of x. Okay, so when I say f of x, so you can use directly dou square f by dou x square, d square f by dx square, so which is only function of x. So that's why we call it as a 1D equation. Okay, so 1D ODE equation. Now, so what is happening actually? So when you use ODE equation, so the flow parameter is depending on only one independent variable, which is either x, either y, either z. Okay, and when I use partial differential equation, so it is depending on both time derivative, with both depending on time and space, which is x, y and z. Okay, so therefore we need to employ this partial differential equations for fluid flow. Why? Because when you take any space, okay, any empty space or any coordinate, let's say an empty room, so you take air molecules, so you take different air molecules. Okay, so you have different air molecules, so which will not remain stationary, so they will vary with respect to time. So let's say you observe starting from t is equal to 0 seconds. Okay, and you take it till 10 seconds actually. So t initial, t final actually. Okay, so when you see the between time interval 0 to 10 seconds, so this, let's say this is fluid molecule 1, and this is let's say this is 5, let us take. So after 1 second, this 1 will not remain here, it will go somewhere this position, and a new position 1 star will come. So this 5 will not be here, it will go somewhere here, and you'll get 5 star somewhere here, let's say. So what is the meaning here? So with respect to time, the position of the fluid particle is changing. So here I have just drawn only some fluid particles, but in reality there will be some million trillions of fluid particles which you see in the empty space. Okay, now so what happens actually, as the time progresses, the collision between these molecules will give rise to the change in temperature, the change in velocity, and the change in pressure, and the change in density. So therefore these flow variables, basically temperature, velocity, pressure, density, so they depend on time as well as space coordinates. So t of so temperature x comma y comma z comma t. So velocity x comma y comma z comma t. Similarly pressure, so which is x comma y comma z comma t, and similarly density, so which is x comma y comma z comma t. So these things, so what you are seeing actually, the flow variables are changing with respect to time and with respect to space. So therefore what happens actually, we need to correlate, or we need to develop a mathematical model so to relate these flow variables in terms of partial differential equations. So that is why we use a partial differential equation to relate these flow variables with respect to the time and with respect to space actually. So that is the major significance, and why we will actually learn the partial differential equations. Basically engineering students, they learn the mathematics in the very first year itself. They learn the matrices, they learn the partial differential equations and ordinary differential equations. That is because, so in every field of science and technology you take, so whether it is aeronautical, aerospace, whether you take any electronics or electrical, you take any field of science and technology, so whatever the governing equations they write, so they will be writing in form of partial differential equation and ordinary differential equation. So in order to solve those equations, some mathematics background is required. That is why it is mandatory for engineering students to learn the partial differential equations. So here in the aeronautical field, so for the computational aerodynamics, so we are using the partial differential equation to govern the fluid flow, so which is to observe the fluid motion from one point, or let's say one station to other station. So for that we require the governing equations, which we have seen: continuity equation, momentum equation, and energy equation. So those equations are written in terms of partial differential equations. So we'll just again see the basic equation which we have written. So dou square f by, so dou x square plus b into dou square f by dou x dou y plus c into dou square f by dou y square plus d into dou f by dou x plus e into dou f by dou y. So plus like let's say you have constant g, so which is equal to, let's say, h. So this thing you can do it now. So we have, let us write the basic continuity equation. So dou u by dou x plus dou u by, sorry, dou v by dou y is equal to 0. So this equation is basically a 2D steady incompressible equation. Okay, so 2D steady incompressible flow. So what happens actually, you can see that, so when we write a generalized second order partial differential equation, so we can deduce that to our governing equation actually. So now, so we will actually see how these partial differential equations are categorized. Now what we do is like we take a discriminant form of this equation. So we will relate so I think you know discriminant d, which is equal to so roots, sorry, here the roots f1 comma f2. So let's say minus b plus or minus under root of b square minus 4ac by 2a. Okay, So there will be a two waves actually. So why? Because when we say a second order PD, so there will be two roots, or let's say in terms of CFD, if we talk, you will have two characteristic waves actually. Now, so we will actually focus on this thing. So why? Because so we have a square root discriminant, which is d is equal to, so b square minus 4ac actually. So which is giving rise to an important conclusion where, so if the value of b is less than this 4ac, so what happens actually, so this will become an imaginary root, okay. And if this value of b square is greater than 4ac, so then what happens actually, so it will give a real and unequal root. So when it is equal to 0, what happens, it will give you one root actually. So we'll see the cases. So what is happening? So again we'll write, so basically discriminant, so which is under root of so b square minus 4ac. So if you take, so let us take this thing. So if b square minus 4ac is less than 0, so when it will be less than 0, so the b square value, so the b square value is less than 4 into a into c value, okay. So in this scenario, so we have a complex roots, okay. So we have complex roots. So when we have these complex roots, so we say that the equations whatever we form, or whatever the flow field we get, they are coming under elliptical equation, okay. Okay, so these are coming under elliptical. Now, so when this b square minus 4ac is equal to 0, so what is the meaning actually? So the b square term and this 4ac term both are equal, that is why it is coming 0. So then it is called parabolic. So then it is called parabolic equation. Next, so we have one more thing, so which is b square minus 4ac is greater than 0, so which is called hyperbolic equations, okay. So in this case, so here what happens actually, so when b square is less than 4ac, so you have two complex roots, so which is in terms of plus or minus I, imaginary roots you can say. So here we have two real and distinct. So here we have one root actually. So here we have one root, here we have two imaginary roots, here we have two real and distinct roots. So what happens actually, so when this discriminant is less than 0, so we say it is elliptical equations. So in the realistic scenario, so we can relate an example. I told you, water you can see, so or it's a sound wave which is transmitted, so in terms of wavefronts, okay. So let's say this is like still water. When I have thrown a stone here, so what happens, this wavefronts will actually travel at a different speeds actually. So this transmission will happen. So the elliptical equations are the equations where the sound wave speed is greater than the body speed actually. So this will come into picture. So the speed of sound is infinite. Infinite in the sense, let's say the sound waves will travel faster than the object velocity actually. So when I say the parabolic equation, for the parabolic equation, I say that so it is equal to 0. So then what happens? So we have one distinct root, and here it is near sonic actually. So basically the transonic problems, whatever the zones we say, lower subsonic and higher hypersonic, so or let's say lower supersonic, these things will come into picture, okay. So the oscillations, the transonic oscillations and the unsteadiness, So basically the unsteadiness will come into picture for the parabolic equations. And while coming for the hyperbolic equations, so this actually is applicable for the supersonic and hypersonic cases. Why? Because so here you have, let's say you have two wave equations. So let's say these two wave equations. So here this is the affected flow field. So outside this flow field, so this zone is called zone of silence. So there is the zone is unaffected. Okay. So basically, when you want to relate these discriminants, the let's say case 1, 2, 3 with the Mach numbers, or let's say with the flow field phenomena, the first one will go into the subsonic, or let's say the low speed flows, and the second one will go for the near transonic zones, or let's say near the upper subsonic zones, and the third one will go for the hypersonic flows. So why? Because so for the first one we say that the speed of sound is infinity. So when the roots are coming as imaginary, so the object velocity is very negligible compared to the speed of the sound. So the sound wave will travel with very high velocity, so where the object velocity or the flow velocity is very less. Okay, so in the second equation, so basically we say it is unsteadiness, so the time dependent parameter actually. And the third one, even the third one is all time dependent parameter, but in the second one we actually focus on the initialization with respect to time. And the first one actually we general equation is, let's say, dou square u by, so dou x square plus dou square u by, so dou y square is equal to 0 is a basic example for the elliptic equation. So you can cross check actually. So you can see dou square u by dou x square plus dou square u by dou y square is equal to 0. So if we compare the roots, so let's say dou square u by, so dou x square plus dou square u by, so dou y square is equal to 0. So let's compare the roots. So again I'll write the equation: a into dou square f by dou x square, so plus b into dou square f by dou x dou y, plus c into dou square f by dou y square, plus d into dou f by dou x, plus e into dou f by dou y, plus let's say you take a constant, let's say g is equal to h, you take something like that. Now, so what we have seen, b square minus 4ac, so is the discriminant. Okay, so which is d square. Okay, so here what is b? So which is dou square f by dou x dou y. So if you compare this, so what is the value of the first equation and second equation, we compare it. So what happens? So the a value is equal to 1 actually. So b value is equal to 0 and c value is equal to 1. So here we can relate actually. So this part you see, okay, and you compare with this part. So what happens? A is equal to 1, b is equal to 0, c is equal to 1. Okay, so which gives rise to d square is equal to, so b is 0 square minus 4 into, so 1 into 1. So what happened actually? So the discriminant d square, which is nothing but minus 4. So which d is equal to under root of minus 4. So what happens actually? This will be equal to plus or minus root of 2i. Sorry, 2i, plus or minus 2i. So we have two roots, so which is of d plus or minus 2i. So the meaning of this, so the first equation, the elliptic equation which I have written, so it has proven that the roots are imaginary. So we have the speed of sound which is greater than speed of the object, and we forms a complex roots where the speed of sound is infinity and the object velocity is very low. So the elliptic equation is one of the examples, so which we say that discriminant is less than 0. Okay. So here in this session we have seen, so basically what is the significance of PDE, partial differential equation, and how do we relate it to the Mach number in general we have seen, and we have seen the discriminant, and we have seen the elliptic equation, parabolic equation, and hyperbolic equation, and we have just discussed the small aspects of elliptic equation. So where we have proven that d square is less than 0, so it has formed the complex roots. So where we had emphasized that when the roots are complex, so the speed of the sound is infinite, and it forms a imaginary roots, and the object velocity is very low. It is falling under incompressible flow or low speed flow. Okay, so in the next session we will see explicitly how the Mach number dependency is coming on this partial differential equation, and how do we actually characterize based on the Mach number, and we will see the equations which will govern the temperature and fluid flow momentum equation. So from the momentum equation and from the energy equation, so we will deduce which part is elliptic, and which part is hyperbolic, and which part is parabolic. So we will write down the general momentum equation and energy equation, and also we will see the Mach number dependency on those parts. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.